Swayam Prabha. Digital India. Educated India.
Welcome to the 8th lecture of this course called Mathematics for Economics Part 1. So, we are talking about different kinds of functions. We started with linear functions where the general form is y is equal to ax plus b. Then we have explored some different more complicated forms of functions. We talked about quadratic functions, and we talked about also cubic functions and discussed certain properties of them, also discussed certain applications of these functions. And now we are talking about a general what is known as a polynomial functions. So, we have this general form px is equal to an multiplied by x to the power n, an minus 1 x to the power n minus 1 dot dot dot. The last terms will be a1x plus a0. So, this is a polynomial, and from this polynomial we can define a function which is like y is equal to px, and then we get the rest of these terms. Now, if we consider this to be an equation rather than a function, that is px equal to 0, then we have an equation. Then there are at most n real values called the roots of the equation for which the above is true. Okay. So, this is the definition of roots of the equation. The number of the roots can be at most n if they are real values. If an equation with integer coefficients has integer roots, then the roots must be factors of the constant term. So, let us look at this idea. So, we have this equation n multiplied by x to the power n plus a n minus 1 multiplied by x to the power n minus 1 and etc. The last terms will be a1 x plus a0 is equal to 0. This is an equation, and in the above equation, suppose all the coefficients are integers. So, an minus 1, an minus 2, all are integers. Now, from the above we can just subtract a0 from both sides. So, we get this expression an multiplied by x to the power n plus an minus 1 multiplied by x to the power n minus 1 plus an minus 2 multiplied by x to the power n minus 2 etc., etc., plus a1 x is equal to minus a0. Now, from the left hand side we can take x common, and within the brackets there will be an multiplied by x to the power n minus 1 plus dot dot dot, and the last term will be a1, and it will be equal to minus a0. Now, we know that a0 is an integer because it's the constant term, and all the coefficients, constant term is actually a coefficient in some sense. So, minus a0 is an integer, therefore, x is a factor of a0, because we are talking about the roots which are integers. So, x is a factor of a0. Thus, all integer roots of the equation are factors of a0. So, take any integer root. Obviously, this will not hold for non-integer roots, but if we are talking about only integer roots, then all the integer roots will satisfy this relation, and therefore, all integer roots will be factors of minus a0, and therefore, they will be factors of a0. We come to another operations of polynomials, this is called polynomial division. So, consider that we are dividing this polynomial, right, 3x cube plus 4x square minus 7x plus 6, this polynomial by x plus 2. X plus 2 is also a polynomial in some sense. Now, how do we do that? We do it in the following manner. So, here we are going to divide 3x cube plus 4x square minus 7x minus 6. So, this is going inside, and on the left hand side I am going to divide it by x plus 2. So, the first thing I look for is how can I make x similar to the first term here, right. The first term here is 3x cube. So, if I multiply x by 3x square, I get 3x cube. So, I write 3x square here. Now, 3x square is getting multiplied by this entire term, which is x plus 2. So, if I do that, I get 3x cube plus 6x square. So, that is coming here, and I do the subtraction. Now, obviously, this the first element, if I consider them, they will get cancelled, right, that is by construction. And from the second element, if I subtract 6x square from 4x square, I get minus 2x square, and then I take minus 7x from above, and so the term that I have to divide is now minus 2x square minus 7x. Now, again with the same strategy, I will try to find out that factor which, if multiplied with x, gives me minus 2x square, and that term is minus 2x. Minus 2x multiplied by x gives me minus 2x square, but there is plus 2 also. If plus 2 is multiplied with minus 2x, you get minus 4x. So, subtract from minus 7x, you subtract minus 4x, you get minus 3x. Then I take 6 from above, I get minus 6 here, all right, and therefore, again I have to think about a number which, if I multiply with x, I get minus 3, and that is very simple, minus 3. So, you get minus 3 minus 6, and if you subtract this, you get 0. So, in this particular method, I can divide one polynomial by another polynomial. In this case, there is no remainder here, right, there is no remainder here, it is 0, but this is not automatic. In many divisions there will be some non-zero remainders. Let us take one such example. So, here you have x cube plus 5x square minus x plus 9, this has to be divided by the divisor, which is x square minus 2. So, x square minus 2 is coming on the left hand side, then inside this x cube plus 5x square minus x plus 9, and I deploy the same strategy, which is that I think about that thing which, if multiplied by x square, gives me this first term x cube, and this is very simple, it will be x. So, x multiplied by x square gives me x cube, but then there is minus 2 term. So, minus 2 multiplied by x is minus 2x, and I subtract minus 2x from 5x square, I get this 5x square plus 2x, and again I think of the number which has to be multiplied with x square to give me 5x square, and that is just plus 5. So, you get 5x square minus 10, right. So, you have 2x plus 10. Now, you cannot do anything else with 2x plus 10, because the power of x here is 1, whereas the power of the divisor is 2. So, this will be the remainder here 2x plus 10. Okay, now we talk about another kind of functions. After talking about polynomials, we talk about something called the power functions. So, a function which is defined as the following: f x is equal to x to the power r is called a power function, where r is any rational number, right. So, r could be expressed in the form of p divided by q, right, and that was the definition of a rational number. Now, here there could be some difficulty in interpreting this x to the power r if r is not a natural number. If r is a natural number, then it is easy to interpret x to the power r. Okay. If r is any natural number, right, 2 or 3 or 4, okay, these are natural numbers, then x to the power r is easy to interpret. So, x to the power, let us say 5, that is equal to x multiplied by with itself 5 times, that is x to the power 5. So, as long as r is a natural number, then there is no problem of interpreting x to the power r. But if r is 0 or a negative integer, then what happens? If r is equal to 0, then again it is not very difficult. X to the power 0 is, we know it is equal to 1. And if we are talking about negative power, so x to the power, let us say minus 2, then I can write it as 1 divided by x to the power minus of minus 2. Okay, that is what I have written here. Minus of minus 2 is plus 2, right. So, here you have 1 divided by x square, and x square is easy to interpret, it is x multiplied with x. So, as long as r is 0, a negative integer, a positive integer, there are not much difficulties. What if r is a fraction of the form p divided by q, where p is an integer and q is a natural number? Okay. So, here we are basically approaching the idea of a rational number. So, I can write x to the power r, which is equal to x to the power p divided by q, and then I can write it as this. So, x to the power p whole thing under the brackets to the power 1 divided by q. Okay. So, this is this we can write. Then what happens, that p gets multiplied with 1 divided by q and you get p divided by q. But what is the interpretation of this number, x to the power p whole thing under brackets and to the power 1 divided by q? This is a number which, if raised to the power q, will give me xp. Okay, that is easy to see. You just raise this number to the power q, then q and q will get cancelled and you will get x to the power p. Okay. So, this is we have done it in step by step. So, I have to interpret this number. Suppose this number is equal to small a, which is a constant, suppose. So, x to the power p whole thing to the power 1 divided by q is equal to a, and then I raise the power of both sides by q, then I get x to the power p, and that should be equal to a to the power q. And this is what I meant by this, that the meaning of this is that, right, if it is a, then a, if I can raise the power of a by q, then I should get x to the power p. Graphs of power functions. Now, in this form f x is equal to x to the power r, as r changes, the graph changes its shape. If r is equal to 1, then what you have is f x is equal to just x. Okay. So, how does this look like? It is a straight line through the origin, making 45-degree angle with the x axis, okay, y is equal to x. So, this has a slope of 1. If r is less than 1, then also it is a rising line, but it is no longer a straight line whose slope goes on declining as s rises. So, this is like this, and if r is greater than 1, so the power is greater than 1, then it is a rising line like before, but now the shape is different, the slope goes on rising instead of declining as x rises. So, this will be like this, the slope is going on rising, it is getting steeper and steeper. So, here is an example of how the lines could look like. In the first case, you have r is equal to 1, here you have r less than 1, and here you have r greater than 1. But when I am saying r is less than 1, I mean r is greater than 0. So, but all these lines, you can see they are intersecting at the same point, and that point is 1 and 1. All right, after power functions, we come to a kind of similar idea of a function, which is called an exponential function. If a quantity rises by a constant factor per unit of time, then it is said to be rising exponentially. Similarly, for the decline of the quantity. So, suppose any quantity is rising with time. So, time here is changing, time is the independent variable, but the quantity in question, it is rising with a constant factor per unit of time. So, maybe it is getting doubled every year, right, that will be like rising by a constant factor, or it could be going down by a constant factor also, it can decline, right, and but the decline is also by a constant factor. If that is the case, then we can say that this quantity is rising or declining exponentially. Suppose a constant a, that fixed factor, and capital A is a given constant, then one can define the exponential function as f of t is equal to capital A multiplied by small a to the power t. So, again just to repeat, here I am taking t as the independent variable, it is rising and therefore, this quantity is changing, and if it is changing by a constant factor, we are calling that to be an exponential function. Here in this case, in this particular example, small a is that constant factor, this I will show it in a second. Now, first look at this form and put t is equal to 0. If you put t is equal to 0, then you get f of 0, and that is equal to capital A, because small a to the power 0 is 1. Now, if capital A is equal to f of 0, then I can substitute that here, and I get f of t is equal to f of 0 multiplied by a to the power t. And how do I know that indeed for this function the factor is equal to small a, right? I said that it rises or declines by a factor, and that factor is small a. What is the proof of that? You take two values of the function at two successive times, one is f of t plus 1, and divide that by f of t, and if you do that you will get small a, right. And since small a is constant, so that means from one period to the next, the rise is also by a constant factor. What about the rise and fall of this function? If small a is greater than 1, right, then the function is rising over time, okay, that is easy to understand. So, a is the factor with which the value of the function is getting multiplied in one period to get the value in the next period. So, if a is just equal to 1, then the value will not change, it will remain the same, which means that if a is slightly greater than 1 even, then in the next period the value will rise. So, that is why I say that if a is greater than 1, then the function is rising over time. On the other hand, if a is strictly less than 1 and suppose it is greater than 0, then it is falling over time. So, think about this, that a number is getting multiplied by 0.5. Now, if you multiply any number by 0.5, then it becomes half of the number. So, and again if you multiply it by 0.5, it becomes 1/4. So, it is going down over time. Exponential functions have wide applications in economics, such as economic growth, population growth, growth of savings, this should be off, growth of savings with compound interest rate, etc. So, economic growth means the income of a country grows over time. How do you analyze that? To analyze that, you might be using the exponential functions. Or population growth, population also goes on rising over time, and generally it is seen that over a not so long time frame, the growth rate of population could be exponential with a constant factor, and similarly growth of savings with a compound interest rate. We will see some examples of that. So, here is an example. Suppose the population of India was 135 crore people in 2020 and it is expected to grow at 1.3% in a year. So, what will be the population in the next year? In the next year means 2021. Now, that can be calculated. It will be the population in the initial year, that is 2020, which was 135, plus you multiply 135 with the factor, right. Here the constant factor is 1.3%. Now, what is 1.3%? It is 1.3 divided by 100, and one can take 135 common. So, within the brackets you will have 1 plus 1.3 divided by 100, and if you simplify this, it becomes 135 multiplied by 101.3 divided by 100, and this can be written as 135 multiplied by 1.013 crore. So, this is the population in the year 2021. The next question is, what about the population of 2022, right, if the same exponential growth continues. So, this will be the population of the year 2021 multiplied by this one, this factor, because this factor I am just using the same formula. So, this becomes 135 multiplied by this and this are exactly the same, and so you have 135 multiplied by 101.3 divided by 100 whole square, and this can be written as 135 multiplied by 1.013 square. In other words, each year the population gets multiplied by a constant factor, which is 1.013. Okay, so, this is the important thing. Remember, when we talked about exponential growth, I said that each year the value is getting multiplied by a constant factor, that is small a. Here that small a is this number 1.013. After t years from 2020, it will have grown to 135 multiplied by 1.013 to the power t. So, that was the general form. It was capital A multiplied by small a to the power t. Here small a is equal to 1.013. If we represent population after t periods from 2020 as Pt, therefore, Pt will be the same thing, which is 135 multiplied by 1.013 to the power t. From the above, one can find the doubling time. So, this is an important concept that is often used, doubling time of population. What does it mean? It is the time it takes for the population to double. So, population is growing, let us suppose small a is positive and greater than 1, then population is growing. Growing by a constant factor. Question is, one can ask the question that how long does it take for the population to exactly double? Okay. We can call that time the doubling time. Suppose the exponential function is f t is equal to capital A multiplied by small a to the power t, where small a capital A is greater than 0. Suppose t is equal to 0. So, therefore, f of 0 is equal to capital A. Let the doubling time be t star. We are assuming that the doubling time is t star, which means after t periods, after that is t is equal to 0, after t star the population will double. So, what does it mean? It means that initially the population was capital A, and after t star the population will be what? It will be this. So, this capital A multiplied by small a to the power t star should be equal to 2 multiplied by capital A, because capital A was the original population. Now, if I use this, then capital A will get cancelled from both sides. So, we are left with small a to the power t star is equal to 2. Thus, the doubling time is the power of A such that the number becomes equal to 2, right. This you can see from here. So, suppose small a is given, I have to find out that number such that A to the power that number is equal to 2. So, this is an example. Suppose small a is 1.013. I am using this 1.013 from here. Okay. Basically, it means that population per year is growing at 1.3%. Now, if A is taken to be 1.013, it turns out to be 54. It turns out to be means t star is equal to 54. So, in 54 years, India's population will double if it continues to grow at 1.3% per year. So, that is the meaning of doubling time. Compound interest. So, this is another application of exponential functions. Suppose P amount of money is deposited at the bank at R compound rate of interest, then after t years it would grow to this number. Okay. Capital G is equal to P, P is the amount of money that was deposited initially, multiplied by 1 plus R divided by 100 whole thing to the power small t. If you compare this with this form, A multiplied by small a to the power t, then small a is really 1 plus R divided by 100 and capital A is equal to P. Okay. So, this is how we can calculate the deposit in a bank if we know the rate of interest, if we know the time that has elapsed, and if we know the initial deposit. Now, a general exponential function with base small a, which is greater than 0, can be written as the following: f of x is equal to capital A multiplied by small a to the power x. Remember, here I am not using t anymore, I am using x, because t was time, right, but there could be some other variables also that one could be considering, which is changing and which might be affecting the value of the variable. So, here x is that independent variable, x could be equal to t, it could be something else. Okay. So, that is why I have written here small a is the factor by which the function changes as x changes by 1 unit. If small a is equal to 1 plus R divided by 100 and suppose P and R are positive, then G rises at R% with per unit rise in X. So, just imagine, compare this with this formula, then it will become very clear. On the other hand, if A is equal to 1 minus R divided by 100, so here I am considering basically it could be that R is negative, right. So, instead of rising, if it is declining, if you are considering a negative interest rate, then A is expressed as this 1 minus R divided by 100, and here R is positive, P is positive, then G is declining at R% per unit rise in X. An example is given. In 1900, 5-year plans were introduced in this country called America. The aim was to double per capita income in 1915, that is in 15 years. What should be the rate of growth per year? So, what are we given here? We are given the time frame, right. There are 15 years that have elapsed. We are given the information that in these 15 years the per capita income should double. Okay. So, we have to find out what should be the growth rate per year. So, basically we have to find out the value of the small a. We know the doubling time is calculated by the formula a to the power t star is equal to 2. We have just seen that, right, the doubling time. Here small a is the factor, constant factor. Now, in this particular example, we know that t star is 15, doubling time is given 15. First, we shall find the corresponding small a which solves this one, this equation. So, t star is given, which is 15. On the right hand side 2 is there, which is a number. So, we have to find out small a. Now, this can be done by trial and error. If you have a calculator, very simple calculator which allows you to find the power of a number, then you can find out that if you take small a is equal to 1.047, then 1.047 to the power 15 is very close to 2, the number 2, not exactly 2, but approximately equal to 2. So, our small a is this number. Okay, we have solved that. Now, remember we have just seen in the previous slide that this relationship is there. Okay, a is equal to 1 plus r divided by 100. So, I can write this in this form, a is equal to 1 plus 4.7 divided by 100. 4.7 is therefore the rate of interest, not rate of the interest, in this case it is the growth rate of the per capita income per year. So, this is our solution, which means that this country which adopted the 5-year plans from 1900 onwards and wants to double its per capita income in 1915, in 15 years, it must grow at 4.7% per year. Okay, so far functions for a single argument have been defined, where the arguments and the functions are real numbers, right. A function may have multiple elements which are its arguments, they need not be real numbers. The function itself may not give a real number. So, there could be variations from the original function or original example of a function that we have been talking about. Firstly, the functions may not be real numbers, they may be something else, some object may be, some person may be, and secondly, the arguments may be multiple, right. It is not necessary that there is a single argument or single independent variable. So, there are some examples that I have given here. The demand for ice cream may depend on its price, and that is called the demand function. If you remember, demand is a function of its price. but it may depend also on the income of the consumers, temperature, etc. So, there are multiple factors that might be affecting the demand for ice cream. Okay. So, I can write it like this: D, which is demand, is a function of price, it could be a function of income, it could be a function of temperature, let us say it is TMP, etc., etc. There are multiple independent variables which might be affecting the demand, and so this function is a function of many variables. And secondly, a function may relate each child to its mother. Here neither the argument nor the function take real values. Okay. Remember, a function is not necessarily a mathematical formula, it is just a relation. So, suppose this relation is relating a child to its mother. So, you name a child, a particular child in a class, and relate it to its mother, right, and that relationship itself is a function. Now, here the child is not a number, right, it is maybe a person, or you can say it is a name, right, and the mother is also not a number, it could be name, a person. So, in this case you do not get real values as arguments, nor do you get real values as the value of the function. So, what is the general definition of a function? So, if you have these complications, then how do you generally define a function? Okay, so, this is the sort of general definition of a function. A function from set A to set B is a rule that assigns each element of A one and only one element of B, right. So, you have two sets, these sets could be consisting of real numbers, they may not consist of real numbers, sets could consist of elements general. But what a function does, that it is a rule that assigns each element, means it should include all possible elements in the set A, and it should assign each and every element to one and only one element of B. It cannot assign more than one element of B. So, A is called the domain, we have seen this. So, here A is domain, B is called the target, domain set, target set. A rule assigns a unique element in B to each element in A, and that rule is the function f. So, here you are taking element x from A, and this function gives you a unique element f x in B. And we write this relation as f of A arrow B. So, it is a function from A to B, f is a function from A to B. Other than this term function, the relation is also called a mapping, a transformation, etc. So, other names could also be used. A particular value from B, f x, is called the image of the element x. So, f x is generally called an image or the image of the element x. The elements in B that are images of at least one x in A constitute the range of f or R f. We have seen this in case of our simple one variable function, right, real valued, but that range could be defined in a more general sense here. So, here R f, which is the range, it consists of those values of f x such that x is an element of A. So, R f consists of only those elements of B which are images of the elements of A, right. So, all elements of B may not be inside the range, some of them could be left out. There are functions where each element of B is the image of at most one element of A. Suppose f is an one-to-one function from set A to set B, also the range of f is all of B. Okay. For each element q in B, there is an element p in A such that f of p is equal to q, right. So, you take any element of q, okay, and there will be one element of p in A such that f of p is equal to q. We can define a function g from B to A by the rule for each element y of B, assign the element x of A such that y is equal to f x. Okay. Now, there is one point that I wanted to draw your attention to, that one-to-one functions are those functions where if you take any element of B, the corresponding element of A cannot be multiple. Okay. There should be at most one element of A, it cannot be more than one, and those functions are called one-to-one functions. Each element of y of B assign the element of x such that y is equal to f x. The function g x will have only one element because each element of A map to a unique element of B. So, let me give you an example of what I mean by one-to-one function. So, suppose you have a function like this, then you take a particular value of y, then it maps to two values from the domain. So, this is not a one-to-one function, whereas if you take a function like this, then this could be a one-to-one function, because here no matter what y you take, you map to a unique element of x. Okay. The function g will have only one element because each element of A is mapped to a unique element of B. The domain of G is the entire B, right, because we have seen that in the previous slide that the range of f is all of B. So, the entire set B is covered in the range. So, therefore, it can serve as the domain. Therefore, G is a proper function and G is called the inverse function of f. Okay, so we have defined what is an inverse of a function. So, for a function to have an inverse, it needs to satisfy two conditions. One is that it has to be a one-to-one function, which means for any value in the B, that is the target set, you get at most one corresponding value in the domain set. So, it cannot be more than one. And secondly, the entire set of B, which is the domain, has to be covered by the range. In that case, you can invert the function because every element of B will map to unique element of A, and that is the definition of a function. Okay, I think I will stop here. So, what we have covered so far in this particular module, we have covered functions and it is quite a large module. We covered about 4 lectures in this module. We talked about the definition of a function, we talked about what are called the linear functions, and then we talked about non-linear functions as well, like quadratic functions and cubic functions. We talked about polynomials, and then we talked about power functions, exponential functions. In each case, we have discussed the applications in economics of these functions. And finally, we talked about the general definition of functions, where you do not have a single argument, there could be multiple arguments. And we talked about the case that the values, the elements from the domain and the range may not be real numbers, but maybe something else. So that was the general definition of a function. So we shall end this class now and see you in the next lecture. Thank you.